Okay, thank you. So Dzień dobry, good morning everyone. So I'm Goulven Quéméner from, where is the pointer? No, that's the next slide. Okay, yeah. I'm Goulven Quéméner from Laboratoire Mécoton in Orsay, in France. I'm part of the Theomol team, so I would like, of course, to thank Michal and Simon for the kind invitation for this wonderful workshop. So today I'm going to talk about ultra-cold coherent control of molecular collisions at a Förster resonance, where we will look for controlled interfering pathways of collisional waves to make them interfere, to control the chemical rates of like with constructive or destructive interferences of a collision. And this work has been done by my PhD student Thibaut Delarue. So yes, as we heard many talks during this week on ultra-cold molecules, so I'm going to skip introduction and go directly to the point. So in order to bring you the idea of coherent control with ultra-cold molecules, I'm just going to consider a typical ultra-cold molecular collision. So let's say KRB plus KRB in initial rotational state N1 and N2. In the following, I'm going to consider ground vibronic state, so I'm not going to consider the electronic state. So everything is in the ground electronic state, ground vibrational state. Only rotational state will play. And because this will be in an electric field, I'm going to use projections Mn equals 0 for the reactance. And then after a collision at, let's say, 500 nanoK, KRB can end up in a final rotational state N'1 and N'2, giving rise to elastic or inelastic collisions here. Or they can end up in pairs of products of K2 and RB2, which is called reactive collisions, and this is sketched here. And so far, studies of KRB collisions in electric field has been done for initial rotational state 0 and 1. So this was done both at the KRB team at GILA, back in 2010 for the first one and 2020 for the second one. So here, technically speaking, I should put a tilde. Sometimes we put a tilde here because we are in an electric field. This is to remind that this is electric field addressed quantum rotational state, but I'm going to skip this tilde in the remaining of the talk. And all the projections here, Mn, are equal to 0. So now, what if now the molecules are prepared in a quantum superposition C00 plus C11 plus C22? That is a Q-treat. So we heard with John Bone and Anna Maria that they use qubit of KRB, so 0, 1. So here the proposal is to do Q-treat 0, 1, 2. So 0, 1, 2 being the rotational states of the molecules. And this will give the outline of my presentation. So first, I'm going to tell how can we prepare those Q-treats, so those individual Q-treats for KRB. Then how will they collide, so collisions of two Q-treats. Then where and when we can get interferences of these prepared molecules that will give rise to coherent control. And finally, I will show you the corresponding rate coefficients. So let's start. So how do we prepare a Q-treat? So that's quite straightforward. So here I'm showing you the energy of a KRB molecule as a function of the electric field. So basically, this is the Stark effect of one molecule in rotational state 0, 1, 2. So in these different colors here. And so preparation can be done at any electric field, but let's take this special electric field here, E star. So where the difference of energy between 1 and 0 is the same as the difference in energy between 2 and 1 here. And this defines the position of a so-called Förster resonance, which, so at 12.506 kilovolt per centimeter, so just right there. And this is really common in Rydberg physics, as we heard yesterday as well. And this has been already observed by the KRB GILA team in 2020. So this is right at this position, you have a characteristic resonance. So then, yeah, at this particular electric field, so here's a sketch of the three energies of the rotational state 0, 1, 2, equally spaced. And if we consider initial molecules in the first rotational state here, the first excited rotational state, so as in this the GILA experiment, well, we can use a microwave and the control knobs like delta, omega, tau. So these three control knobs where delta is the detuning of the microwave, omega is the Rabi frequency of the microwave, and tau is the duration of application of this microwave. So tau is the time after which we cut the microwave and where we let the Q-treats collide. So the corresponding wave function is a quantum superposition. So that's the Q-treat here. So for the individual molecule, it's donc quantum superposition of the rotational state I here, I being 0, 1, 2 with coefficient C1, C0, C1, C2 times the plane wave corresponding to the motion of the molecule in a given state I here. Ki is the wave vector of the molecule in state I, and omega I here it's related to its total energy, so given by its kinetic energy here and its internal rotational energy epsilon I, which is one of these three values here at a given electric field. Okay, so let's put this aside. And so then we have just a 3-level system interacting with a microwave. So we can solve this numerically with time-dependent Schrödinger equation for a given set of delta, omega, and tau. But then it turns out that when delta equal to 0 here, so at microwave resonance, let's say, one can solve this system analytically, and so you can obtain the superposition factor, so the C coefficient, C0, C1, C2, which are given by just this simple expression here, monitored by theta and eta here. So theta turns out to be proportional to the ratio of the dipolar transition between 1 and 2 and 1 and 0. So it's a known number and turns out to be these values. And eta is simply just 0.89 times omega tau, so the Rabi frequency times the time of applications. So for a given omega and tau at delta equals 0, we have a unique parameter eta that I will call it the control parameter that will give you a given triplet C0, C1, C2. So everything is characterized for the individual function. Yes, and here I'm just plotting you what are the C0, C1, C2 coefficient modulus squared. And when eta equals 0 means that omega equals 0, for example, so we have no microwave. All our molecules are in state 1, so this is what we started. So that's just for one molecule. Now we will turn off the microwave at time t equal tau, and then let the Q-treat collide. So when you have two-body collisions, then, well, simply we will have an incident wave function, which will be simply the cross product of the individual prepared molecules. And we end up with this quantum superposition of state alpha. Alpha will be just a combined molecular state made by all the combination we can make from our microwave preparation. So namely, a combination of state 0, 1, 2. So we'll have 9 states, 9 possible combinations, but we will take only 6 of them due to symmetrization reason. So we'll end up with all these combined states, so 0, 0, 1, 1, 2, 2, 0, 1, 0, 2, 1, 2. I put a plus here, so this is just due to the fact that we use a symmetric state. So for example, 0, 2 plus is 0, 2 plus 2, 0. So it's an entangled state. Same thing for 0, 1 and 1, 2. Okay, so we have everything here. We will have a superposition factor coefficient that I will show you just after. And then we have 3 other terms here, which correspond to the plane waves of the two-body motion. So the first one here, this is related to the relative motion between the two molecules. So described by the distance r and little wave vector k. The second one is the plane wave associated to the center of mass of the two molecules. So associated with the distance capital R and wave vector capital K. And finally, you have the time dependence of the wave function, so which is related to the total energy h bar omega, which is the sum of the kinetic energy of the pair, of the relative motion of the center of mass motion, and the internal energy of the two molecules. So epsilon alpha is the energy, is the internal energy of the two molecules, so which I showed you here for a given electric field. So we have 6 states, and we have the evolution of this internal state as a function of electric field. And you can see at the Förster resonance, E star here, there is something interesting. The energy of 1, 1 is equal to the energy of 0, 2 plus here. So this will be important for coherent control. So I will explain this later. Okay, and then finally, the superposition factor. Well, we can show that they can be expressed by the C0, C1, C2 coefficient of the microwave preparation. So by all these expressions, so we can plot for our control parameter of the microwave all these C alpha coefficients. So we have everything we need. So that's at the beginning of the collisions. After a collision, they will be scattered. So what we have to cover is not the incident wave function, but the collisional wave function. So this is the usual expression that we have in theory of collisions. We recognize here the incident wave function with the center of mass plane wave here. But here I have included now the scattering wave function, which is a sum over alpha prime, so sum over all the final combined molecular state possible without restriction. And this is what we will observe after a collision, times the outgoing spherical wave, so that's the scattered wave, times the superposition factor C alpha, and times the so-called scattering amplitude to go from initial state alpha to final state alpha prime. So these scattering amplitudes, we have a code to compute them for the reactants. So we know what to put here for each initial state alpha going to each final state alpha prime for the reactants. Okay, so except at E star here, so just in other arbitrary electric fields, there will be 6 collisions. So yes, this sum star, this means that we are summing from all the initial states, or from all these 6 states here. So there will be 6 collisions of 6 initial states in 6 independent center of mass frames moving in different ways here. So this is due to this term. So all of the molecules will move in different ways because especially of this term, omega alpha here, related to the internal energy of the pairs. You see that all the internal energies are different. So there will be, so all the center of mass will move differently. At least they will not be synchronous. Or synchron, I don't know. So, and in this general case, well, the rate coefficient, so something that you observe in an experiment. So it's so I call that beta QS for quantum superposition. So to end up in a final state alpha prime as a function of collision energy, is this special sum over all our 6 initial states of the state-to-state rate coefficient, so from going to alpha prime here, which are given by this formula here. So everything is known, but this is proportional to this TQS modulus squared, where TQS is just the weighted value of the T matrix, T here, weighted by the superposition factor here. So the T matrix is related to the S matrix that Timur just talked just before, and this is related as well to the scattering matrix. So our code, our numerical code, can provide this T matrix element for the reactants. But you see that it will be just a moduli squared here of the rate coefficient. So that will be just a weighted sum of the rate coefficient. So there is nothing special here. This will be just the sum of the T square. So no interference term appearing here. But now if you are at the electric field, the special electric field E star here, we can show that the relative and center of mass frames of 1, 1 and 0, 2 plus move in the same way. So this is shown in our paper in the supplementary material. But so we'll have, due to this 4 condition, so we can show that the relative motion between 1, 1 and 0, 2, the relative motion between 1, 1, the wave vector of 1, 1 and 0, 2 are the same. The center of mass wave vector of 1, 1 and 0, 2 are the same as well. And because we are at E star where the energies are equal here, so we have this relation here. And when you plug into this formula, you see that these 3 elements are the same, so that the total energy for a pair colliding in 1,1 is the same than the total energy of a pair colliding in 0,2. So then here we will be able to factorize many terms here in the wave function for 1,1 and 0,2. So yes, this is here. So let's factorize this, and this will bring where interference will occur. So this is now after factorization we get an interferential term. So I call that Psi in. So here is the incident wave function, but then you see that we have factorized the same center of mass of 1,1 and 0,2, the same time dependence, and the same outgoing spherical wave. So then we can just add, so for a final state alpha prime, we can just factorize the scattering amplitude with this superposition factor C11 and C02. So yeah, this is what we have done here. So we can define the scattering amplitude for the quantum superposition states, and similarly the T matrix elements, which are just the weighted sum of these scattering amplitudes and T matrix elements. So the T matrix elements here, we cannot change them. But what we can change or control is this C11 and C02 coefficient. Generally speaking, these C11 and C02 coefficients are complex numbers, so we control them with our microwave. So then we can have any number that we want for the TQS matrix elements. So this is the basis of coherent control. Yeah. So and remember, so the rate coefficient is the modulus square of the TQS matrix element. So that will be the square of this sum. So this is what helps here. That will be the square of the T sum, and then this is where obviously interferences will come in the rate coefficient. So this is the principle of coherent control, so largely studied and pioneered by Moshe Shapiro and Paul Brummer back in the 90s. Also recently studied by Adrien de Volder, Paul and Timur recently as well. And in their review paper here, they said that okay, control can be achieved by manipulating quantum interferences that arise when the desired final state is reached through a number of indistinguishable pathways. So our desired final state will be the observation of a pair of colliding pair, alpha prime here in an experiment. A number of indistinguishable pathway will be, so we have two pathways indistinguishable with the same energy, 1,1 and 0,2 plus, because they have the same energy as well. So because they have the same energy, we can factorize the wave function and we get this interference term when we squared the modulus squared. And we can manipulate them with this C11 and C02 factor with the microwave. So and yeah, this is the sketch of this. This is the reason of this figure. So we have pathway 1, pathway 2 that can be controlled with parameter A and B. They will the collisional waves will interfere. You can add the collisional waves, and when you take the square of it, you can control the rate coefficients with constructive or destructive interferences. Okay, so now I'm going to the final slide. So that's more of the results. So here we are at Förster resonance of 12.505573 kilovolt per centimeter, a collision energy of 500 nanoK, and we are in free space. So that's the same experimental conditions than in the GILA experiment. And so that's the rate coefficient as a function of the control parameter eta for the final state 0,2 plus and 1,1. So we have to compare them with the dashed line as if they were non-interfering. So if we took only the sum of the t square, and we see that for a given eta, well, 0,2 plus has been increased, 1,1 has been decreased due to constructive or destructive interferences. So here I'm showing you the rates of the other states. I'm going to skip a little bit. And yeah, so something I did not have time to talk is this is the overall reactive rate. So these are non-interfering, and this is due to us theoreticians that we cannot predict, as Timur mentioned, we cannot predict the T matrix element of the final chemical reaction. We will need hyperspherical coordinates, and I think the code does not even exist for four atoms. Yes. So then they are not interfering, but however, the state-to-state reactive rates are expected to interfere. So us theoreticians, we cannot predict them, but the experimentalists can measure this state-to-state rate coefficient. And for example, in the KRB Harvard experiment in Conquen's group, They have done that already for the zero electric field. So here is all the reactive probability for K2 and RB2 here. So now, if they could do this experiment at E star instead of E0 for different values of the microwave preparation, well, this will bring coherent control to the reactive state-to-state level. So you will have each of the rate coefficients for each of one of these columns here. Okay, so from this experimental observation, we could infer each theoretical individual state-to-state elements of the T matrix, or if you want, each element of the scattering phase shift of a chemical reaction. So this could envision what John Bone, Anna Maria Rey, and Junier like to call in this review complete chemical experiments. So this was as well said by Timur as well, where we could ultimately know all the elements of the T matrix or the S matrix, so including the norm, but as well the phase of the matrix elements. So due to a kind of this interferometer experiment. I'm coming back to this slide. So final point, one can have high productions of ultra-cold entangled states, 0, 2+. You will see that the rate is very high here compared to all the other reactants state here. So here it's, for example, 3 times bigger than 1,1. But then one can tune, so we can remove this constraint delta equals 0 here, and tuning delta omega tau to optimize coherent control to produce even higher production of entangled states due to collisions. And this is what Thibault has done here. So here, this is the branching ratio of the 0, 2+ rate over all the cumulated rate of the other reactants. And so for, let's say, omega equal 20 megahertz, let's say microwave preparation of, let's say, 400 nanoseconds here, and detuning of 30 megahertz, well, you have this yellow point where the rate coefficients are 50 times more than all the other rate coefficients. Okay, so time to conclude. So we showed that microwave preparation of dipolar molecules in Q-treats at a Förster resonance could set the condition for interferences and coherent control of their dynamics, enhancing production of entangled pairs, and inferring the phases of the T-matrix elements of a chemical reaction. So that's very nice. That opens a lot of perspective to the field, but this is a theoretical proposal. So what is the experimental price to pay for that? And here in this paper, we said that, well, we should be at right at the Förster resonance, but how right is right, right? So you see here, I put 6 digits after the electric field here. So to avoid the dephasing of the superposition factor over space and time, one needs ultra-precise control of electric field. So we estimated for that, for a typical optical dipole trap, that we have to be precise up to the millivolt per centimeter. So that's why I put 6 digits here. So I ask you during this week if it were ever possible, and you tell me, most of you told me that it will be very challenging. So I guess that's a polite way to say no, it's not working. So either we wait 20 years, like the fielding state, and maybe in 20 years this will be possible. So I was a bit desperate, but then Anna Maria came on Wednesday and she gave me a tip. And what she advised is to apply the non-precise electric field, so let's say 12.5 kilovolt per centimeter. Then it will not be matching, the energy will not be matching, but we can cover the remaining of the matching using the magnetic field and hyperfine structure to fine-tune the remaining energy. So this, so I will have to come back to Orsay and put the numbers on this, but we will see if this can be possible as well. Okay, so before stopping my talk and still speaking about precision, just would like to advertise this open tenure track position in experimental quantum science at CNRS. So this is, the title is Precision Measurement for Fundamental Physics, and this will be devoted to one of these 3 labs in the Paris region, including our lab at Laboratoire Mécoton. So yes, so if you have interested, please look at this, the link here of the website, or contact me for more details. And with that, I will thank you for your attention.
All right, nice talk, Goulven. So I think with all these proposals, and of course, the degeneracy condition
Yes,
that you
that's the
mentioned,
hard,
but
yeah.
there's also symmetry constraints. For example, we have shown in some of those
Yep.
papers that you showed that the total internal projection of the first molecule plus internal projection of the second molecule must be equal to the, of these two superpositions must be the same. So when you have two
Yes.
superpositions, the M12, which is the total internal angular momentum projection, has to be the same. Otherwise, of course, they're in different symmetry sectors, they will not interfere. So when you're doing this hyperfine and stuff like that, I think it would be really important to check the sum of those
Yep.
projections to ensure that they match. Otherwise, they won't interfere, and it would be like not so useful.
So at 500 Gauss, like a typical magnetic field at KRB experiment, I think the nuclear spin is almost a good quantum number. So for the zero state, let's say, for the one state, so the thing for finely tuned, they need not to have the same Zeeman curve, because otherwise you will not be able to shift. But it turns out there is hyperfine couplings for the rotational state. So I think it's the electric quadrupole moment with the gradient of the electric field that shifts a little bit, and the Zeeman effect of 0, 1, and 2 are slightly different. So when you make the sum of them, you can, I think, just sum the fine detune it. So, but there will still be a good character. Oh, sorry. There will be still a good character in, let's say, the -4 1/2. So yeah, you will have 95% of -4 1/2 and 5% of another state. So this one will not interfere. But then you will still have this 95%. So it will reduce a little bit the value of the scattering amplitude. So that's why I have to put some numbers to get back to this.
Okay,
Yes.
so you thought about this.
Yes.
Yeah. Okay.
Normally, yeah, I don't see. I'm quite hopeful for that. So it will just reduce the intensity, I think, of the. Yeah, I have to check.
And I must say, we also had a similar proposal for coherent control with magnetic fields in 2023, and we talked with atom ion people about that, and they said magnetic field control to that level, just like you said, would be impossible. So forget about it. And so we thought zero field experiments would be promising. So how can you do something at zero field?
The problem with zero field, I think the 0, 1, 2 will have, so you will not be in the good, the nuclear spin magnetic moments will not be good quantum numbers. So I'm not sure.
You have other quantum numbers like F. Total.
Yeah, and you will have this. So yeah, your question is, does the Förster resonance survive in zero magnetic field, or?
Yes, something like that.
Yeah, I'm afraid of the hyperfine coupling things will probably destroy the things. So it's better to be at high magnetic field to have good nuclear spin numbers. They are slightly different because of this hyperfine couplings. So I think it's better to be at high magnetic field. And what we need to cover here is, it's like some hundreds hertz. So I think hundreds hertz, maybe kilohertz. So this is maybe what the magnetic field does at this magnetic field. So I have to put some numbers on this, yes.
Okay. Thank you.
Yeah, so maybe I don't fully understand the idea of the magnetic field compensation, but typically what we have in the electric field is like, I think on the order of 10 millivolt per centimeter noise fluctuations over the entire frequency range. So these are just fluctuations. So would you be able to compensate for that with a magnetic field then, if you really need to be at the Förster resonance?
So if we compensate with the magnetic field, I will not care about the electric field anymore. So I will be at 12.5. You mean you will always have this kind of things? This is what you said?
You always have fluctuations in the electric
field. Okay, I see. But this is related to the fact that the electric field will not be uniform anymore. Is it a question of uniformity of the?
It's just noise on the power supplies.
Okay. Yeah. Well, then I will have to think about it. So yeah, that's the price to pay if you want to see coherent control with ultra-cold molecules. This is what I will say. With yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With, yeah, so the, you will have this kind of things. This is what I will say. With Yeah, but then you have the hyperfine coupling, so it's very hard to find degenerate states at zero field. So accidental one, or but then you need couplings. So you need a T matrix element that will go from 1, 1 to 0, 2. Otherwise, if it's 0, then your T matrix will be 0 and you will interfere nothing. So that's why the Förster resonance is nice, because you can control, you can make on purpose where they are going to cross. Oh, with gradient possibilities around the Förster resonance. Okay. Okay. So you see, Anna Maria saved my life. So that
I also think that even if you park at the Förster resonance, you have these fluctuations. If the enhancement of the rates is strong enough, you just blur, and then you don't get the enhancement as much as if you park perfectly. You still get an enhancement, but then it's the question whether it's detectable.
okay. Yes. Okay. Okay.
All right, I think we have to go to next talk due to time limit. Thanks, Goulven.
Yep.